All right, so the next problem is directly related to this equation. So when I say this equation, I'm talking about equation number 9. It also relates to equation number 10. And so we will need to know the accelerating voltage, the the deflection, and so delta y is the deflection or the vertical distance. So that's the deflection, and delta x is the length of the parallel plates. So let me just go ahead. This is the problem. You apply an accelerating voltage of 970 volts to an electron gun. The electron leaves the gun and passes between two parallel plates that are 17.9 centimeters long and have a voltage difference of 1620 volts between them. If the electron is deflected by 12.05 centimeters after passing between the plates, what was the electric field strength in this region? And so you can see right here that we have the electric field strength. So all we need to know is the accelerating voltage, which is here. We need to know our delta y, which is the vertical distance, which is here. And that's just really our deflection. And then we need to know our delta x, and that's the length of the actual plate. And you'll see that I'm putting these in meters. I'm converting them over. Or so you'll see the charge on the electron. We have that, and then we have our mass of our applied voltage. We have the distance of travel for the electron, and then we have the deflection, and we have our. So those are in centimeters, as you can see right here. And then we just convert them over into meters here, okay? And you can see that on the other sheet. And we have ourselves a plate voltage, all right? And so this is not electric field, but electric field. All right. So let's see how we calculate this. So we can see right now that we don't have enough information in here. So let's go ahead and do that. So we have 4 times the, let's see if C is the accelerating voltage, applied voltage. Okay. So I really wish I'd have called that accelerating, but I can do that later. So that's applied voltage. And we are going to multiply that times 4 and then multiply that times the deflection. Mm, all right, so that's our deflection or the delta y. And then we want to divide this by the distance of travel squared. All right, so here is our electric field. Now let's go ahead and find the effective distance. And so the effective distance, if I go back to the theory here, the effective distance is, and let's go up to this equation. It is the plate voltage divided by the, so it's going to be the, I'll just write that equation down. And let's pop a new sheet in here. So you guys can see that it's pretty easy. If I go ahead and grab this is our electric field strength times our plate voltage over the effective distance. All right. And that's the plate separation. So this equation actually implies that the effective distance is just equal to the plate voltage over the electric field. So we just calculated the electric field. We know the plate voltage, so we can calculate the effective distance. Let's see what it's going to be. All right. So I'm just going to say equals to, and then we need to find the plate voltage, which is here. 1620, and we want to divide that by the electric field. Okay, and so the effective distance is, uh, no, it can't be in 11, it can't be centimeters, this, because I've converted everything over to meters, so this is meters. But we do need to convert it over to centimeters, or, I could do this. I could leave it like this, and then I could just multiply this times 100. And then we just avoid an extra step. So this is what, 11 centimeters.